So I think let's start with talking about the halvening. So I'll share my iPad here. So let's discuss this a little bit. So we had Bitcoin halving. So what does this mean? I've written down several questions. So let's talk first about the first one. What is it? So when we talk about a Bitcoin, then you know the most known thing, the most known fact about Bitcoin is that there are actually 21 million Bitcoins in total, and there can never be more than that, and it's a fixed amount. So the currency itself is deflationary. So it can only increase in price in terms of the scarcity gets higher and higher, but there is no way to produce any additional Bitcoins. And to ensure that this number is ever kept or this number is consistent, there is this process called halving. And halving basically is a process I'll go in detail in a second. So first of all, to understand this, we need to get an idea of how money comes into the system. So this is something we did not cover right now in the lecture because we talked a lot about the exercise, the transactions per se, how the transaction itself work. But there is one special transaction, and that's the so-called Coinbase transaction. And this Coinbase transaction has something very special because when we look and when we remember our slides, we always have some kind of a transaction, and we have some inputs here, and we have a number of outputs here. So this is to ensure basically we have some money in here basically to say, and we have some money going out there, so to say, and this is to ensure basically that the inputs, the sum of all inputs, has always to be greater or equal the sum of all outputs. Why is that the case? Very easy, because we do not want to spend money we do not have. So you can imagine that I want to pay to you 10 Bitcoin, but I only have 5. So this transaction should definitely be invalid because we're creating money out of thin air. So there is one special transaction, and this is the Coinbase transaction, where actually we create money out of thin air. So we have a transaction again, but in this case, this transaction has no inputs and several outputs. So and this is sent to some address. I don't know which address. We don't care right now. So why is this Coinbase transaction allowed to have no inputs? Because it's the first transaction in your block, and it contains the mining reward. So this one is consisting, so the money where this basically comes from, R2, it's first of all the mining reward, and we have a transaction fee. So the difference, so if you go here and look at the delta between these I and O, then this is a transaction fee. So the money you pay the miner for him to include your transaction in the block. And this is the transaction fee here. This stems from this one. And this is the interesting part we take a look right now. So the mining reward is basically a bonus for the miner to that he decided, okay, I'm doing the proof of work, the cryptographic hash puzzle we did in the last exercise. If they solve it, if they invest the mining power, if they invest the hash the hashes, and then they get rewarded. Maybe if they find the block, if they solve the puzzle. And this mining reward is strictly defined per block. So we started with block 0, obviously. I can't write today. I'm sorry. Can I do some kind of more grained? Wait, let's take another. Okay, doesn't work like that. So we start with block number 0, where it was 50 Bitcoins. So we can quickly check that in our browser here. So So let's take a look, for example, at the block 500 here. So this is block 500 right now. And to get it a little bit bigger. And we have a generation of 50 Bitcoins. So that's block 500. That's how it works. So if we look back now at our at this one here, then we have this fixed 50 Bitcoin for 210,000 blocks. So every 210,000 blocks, this mining reward gets halved, as the name says, halving times 0.5, and so forth. So we have 420, 1, 2, 3, 12.5. So this was the current amount we had last week. And on Monday, like 9 o'clock in the evening, we reached a magical blocks 630,000, resulting in a new value called 6.25. So again, halved. And this is something so special and so rare because you maybe know this from the lecture. I think Professor Mattes has mentioned this. We have 210,000 blocks, and one block takes roughly 10 minutes. So each of you can sit down and calculate how long this takes to get 210,000 blocks. And it's roughly 4 years. So in the whole series of blockchain-based systems engineering, I'm doing this since 2018. We never had a halving together with our students, so to say. And so that's a very rare occurrence here and has obviously a larger influence on the overall network. So if you think this further and further and further, so what is the implication here? This will get, so 3.1.0 something like that. So this will get smaller and smaller and smaller. So the mining reward gets smaller and smaller and smaller. And this is a very, very rare, that's an interesting question. How do you deal with that? So before we go into this, how this will affect the network long term, let's take a look at how this influences the network short term. So what is happening, or what happens after that? So the idea is there are two topics we have to talk about. First of all, price, and second of all, hash rate. Why these two? So first of all, you could talk about the price. Why? Because the Bitcoin price, as every natural good or every good, the price is determined with supply and demand. So the more is offered and the lower the demand is, the price goes down, so to say. And it's interesting because miners run facilities. These are businesses. These have costs like labor, they have hardware, they have energy costs, stuff like that. And they need to pay the people. and or pay their energy provider, stuff like that. And therefore, this is a consistent stream that miners, when they get their revenue, these 12.5 bitcoins or 6.25 bitcoins, they usually sell it pretty fast because they want to have bucks on their hand, they want to pay stuff. And that is basically pushing, that is increasing the supply. So the supply goes up because every 10 minutes you can think about it times 24 hours. That's a lot of money that goes into the system. So you have to calculate it yourself with the current price. Times 6, obviously, for each hour. And so this increases the supply. The demand itself is more like, we don't know. So demand should stay identical or is relevant because of, it depends on what's going on, is it mentioned in the news, stuff like that. So that's very irrational. We cannot really think about that. Also, the supply is highly irrational, but that's just we're just talking theories here. Yeah, it's nothing proven. It's nothing that we know for sure. And if these 12.5 Bitcoin now go to now move to 6.25, then the supply should decrease. That's the initial idea. And if we look, for example, at our highly famous CoinMarketCap, so let's switch back to the browser here. Then you will see that Bitcoin is roughly at 9,000 euros dollars today. And if you look at like the last 7 days, and you look on Monday, it was like 8.5, and now it's 9,000. So it's a question if this is a very short-term influence or more a long-term influence. So definitely long-term influence, because you need to wait several time. So you need to wait 100 blocks before you can actually access or transfer the money you got per mining reward. But as you saw here, so it crashed from almost $10,000 down to 8.5 again. So it's very volatile. It's a very, very fragile development here. And to go at the other, go back to the hash rate, or what happens on short term with the hash rate. I think it's very interesting to think about, okay, so hash rate is determined by companies. They provide hash rate and they get a revenue for it. So if you think, if you have like 10% of the hash rate, of the overall network hash rate, then you receive like 10% of all the Bitcoins. So so that calculation we had up here right now in terms of 12.5 times 6 times 24, that's roughly your revenue. So, and also here we what happened here again? I don't want this. Can I remove this? Thank you. If you go down here to 6.25, then obviously your revenue is going to be only the half. So also the miners only really lose a lot of money here, or lose a lot of revenue here, and that definitely leads to that if your mining hardware is not profitable. So it could be the case that so this revenue here, so revenue is, so it's you have revenue, so you have so I'm not sure if this is the correct terms here. In Germany it's easier. So this is basically the Umsatz, and so to get your gain, it's basically revenue minus costs. And if your revenue goes lower than that and your costs are higher than your revenue, then you're making a net loss, and then obviously you go out of business. So what we should see is that miners who are not as efficient as other miners will go out of the market. So the overall hash rate is likely to go down here. But very interestingly, let's take a look at how this hash rate has developed in the last 3 days and see if our assumption here is true. So we looked at that one here. We go back to Bitcoin and we can see here some kind of exactly. So we have a difficulty. This difficulty was that's a little rather, so it's going up obviously. I'm looking for a I need to search that for 1 second. We had some nice slides about that. Okay, no worries. So the difficulty itself, you did not see that actually, I'm sorry. If you look here, then you see that this is our current difficulty, and this difficulty is calculated every 2016 blocks, which are 2 weeks exactly. And you see the next estimated difficulty is about 2% higher than in terms of the before one. So since 2 weeks, because the next readjustment is in 5 days, so 9 days was the last difficulty adjustment. So since then we had a 2% increase. So we will see if this goes up or down the next few weeks. Currently it does not look that way, but we have to check, and we will get back to this and talk a little bit about that. But that's actually what happens with the hash rate here. Let's check some tweetback questions before we move on to the long-term effects. I think that's also interesting for you. Could you give a small summary of what miners do to verify blocks? So in terms of verification, that's the part before you. So everyone has to do this in terms of full nodes or miners, so we don't care who does it. And there are some key ingredients. I think 2 of them are. So first of all, we validate if all transactions are correct. So do they spend more money than they are allowed to? Is the money already spent? Stuff like that. Are the transactions valid? That's the first thing. And the second thing is the proof of work properly solved? So in terms of the new block is created, links to a previous block, and on top of that is the proof of work in terms of this hash puzzle we showed in cryptographic basics. Is this properly solved? And obviously you have to check integrity. Is all other stuff correct? That's obviously also the case. It needs to be the case. But apart from that, I think proof of work and transaction validities are the 2 most important things. To the mining, so for every block you mine, you get roughly 60,000 euros. Is the electricity bill that high, or why isn't everyone doing mining then? So that's exactly the case. $60,000 per block. So go in, join the race. No, it's absolutely batshit crazy. So if you want to do this, you need extreme cheap electricity. So we're talking about 1 to 2 cents per kilowatt hour. In terms of you pay in Germany, here I pay with my electricity bill, I think 27 to 30 cents per kilowatt. So it's like 15, 20 times higher than it needs to be. And also the hardware is quite expensive. So you cannot do it with your computer, not with the graphics card. You need specialized hardware to do that. Question, so there is a fixed mining reward and additional transaction fees that go to the miner. Exactly. So as I said here before, the mining reward here, or the money the miner gets here, consists out of the mining reward and out of the transaction fees. So accumulated transaction fee of all transactions the miner include in its block. I can't explain the price variations. I'm sorry. That's up to the market. Can you repeat what exactly the hash rate is? How is it related to the hashing power mentioned on exercise sheet 1? So hashing power, hash rate, mining power, these are all the identical terms. They mean the same thing because the idea is that you have a machine, and these machines produce several thousands, millions, billions of hashes per second. And overall, the network produces like, I think, 10 exahashes per second. And that is exactly what the hashing power is. So the bigger your share is in the network, the more easier you find new blocks, or you're allowed to propose new blocks. But that's also next week. Professor Matis is going to talk about this. It's a little bit out of order right now. Yeah. Also the hash rate and difficulty. So this is also a topic for next week. I will talk a second about it. The idea is we have a network that consists out of an anonymous. This is an anonymous network, so we do not know how many people are in there. So people could come, plug in their hardware, plug off their hardware anytime. We would not know. And this network now needs to be able to produce a new block every 10 minutes. And to establish this, or to ensure that every 10 minutes roughly a new block is produced, we need to adopt this solution, or adopt the requirements for a solution to the current hash rate in the network. So the higher the hash rate gets in the network, the higher the difficulty is going to be. And this is exactly what you see in the here with the difficulty. This is a difficulty, and obviously since the last readjustment, 2% more hash rate has entered the network and works on solving Bitcoin blocks. And to keep this rate at 10 minutes, at roughly 10 minutes, this needs to be adjusted. So it's not always 10 minutes. It's rough. It's on average it's 10 minutes, but it's usually could be 5 minutes, could be 15 minutes. It really depends on the system here. Okay, and yeah. So that's a question I think I'm going to answer right now. So someone asked about how is it going to evolve in the future, and this is exactly what we're going to talk here. So what happens here when the mining reward goes down? What happens when mining reward is 0 or close to? So very good question. Let's switch back here. So there is some idea. So the initial idea was that the mining reward at the beginning is very high and gets very low in the end, because as in the beginning you see blocks, there are no transactions in there. So at the beginning 50 Bitcoin BTC mining reward, and TX fee 0. And this should 25 something here, 12, a little bit more. So the idea is that the transaction fee increases, and this decreases and further decreases until no mining reward is left, and everything miners are only encouraged by mining by including transaction fees. But this is a very interesting assumption, because the transaction fees, if you look at the browser here, again, where's my Chrome? Here it is. If you look at like the last blocks here, like look at this one, we have a generation of 6.25 and a fee of 1.09 Bitcoin. So you see it's 6 times the generation is, the mining reward is 6 times higher than the fees they get currently. So these needs to shift by a lot. But the problem is that there are developments in Bitcoin, for example, Lightning Network, which are leading to a massive decrease in transaction fees. So it's totally unsure if transaction fees will ever be larger than or if they can motivate enough miners to participate in the blockchain here. So that's a very important detail here. And so there are 2 scenarios for that, or a third scenario. This is the first scenario, basically. Second scenario looks like that. We increase the 21 million Bitcoin cap. So we just update a new version of Bitcoin, which says, okay, we lift the mining cap to 50 million, maybe to unlimited amounts of Bitcoin. This is heavily discussed, and this is what I think won't happen, because a lot of people really believe in this 21 million Bitcoin shit. It has become like a belief, or it's really a really strong notion to break with. So this is likely not really going to happen. And the third idea is I saw, and there might be many others out there, is the idea that very old coins, so you have old coins in the Bitcoin network, that miners are allowed basically to take them, because people argue with this, like old Bitcoins they are not used anymore, maybe the keys are lost, stuff like that. And now it's possible to say, okay, let's take these and give this to the miners. So obviously this is some kind of Enteignung, I don't know, so taking money from people away you don't know. Also seems a very controversial solution. So in the end, we don't know. Bitcoin is governed by a decentralized network. There is no real person here anymore who tells us what we should do, and we need to find consensus about what we should do. And it's going to be a very interesting discussion how this moves further, because in the end it could really happen that because fewer and fewer miners participate, the network gets more vulnerable, because we can take over the network with less and less money, with less and less hardware. So this is a really security implication question here. How secure is the Bitcoin network going to be? But apart from that, I cannot really, I don't know the answer. I don't think anybody knows, actually. So we will see, and it's going to be very interesting how this will look like. And last but not least, in the halving discussion, I want to briefly show you one little detail here. The last block with 12.5 Bitcoin here, the block 629,999 had some data stored within it. And this was mined by a pool by the F2 pool. And they thought about, okay, we need to send a little bit political message. We need to include something forever in the Bitcoin blockchain. And what they did, similar to what Satoshi Nakamoto did with in the first block, was they included a newspaper article. And the New York Times on the 9th of April 2020 published with $2.3 trillion injection, Fed's plan far exceeds 2008 rescue. And this is a direct reference to Satoshi Nakamoto presenting or publishing Bitcoin after the financial crisis in 2008. So strong political message here of the Bitcoin community forever put into the Bitcoin blockchain. So that's about that. One small question here: what happens to Bitcoin after all 21 million Bitcoins are mined? So we don't know that, but it doesn't stop. So you can produce blocks with a 0 Bitcoin reward. So there is no limit to, oh, we're running out of blocks or something like that. So you can produce unlimited amounts of blocks, but that's not the issue. So the issue is, can we keep up the Bitcoin network when the incentive for miners to participate in the network decreases to a level that it's dangerous for the security of the network? That's the main reason here. Okay, so I think we should continue here right now. Half an hour already spent talking about the Bitcoin halving. I want to see, okay. Then let's continue with the exercise, I think. That's what you're here for, I think, or not only, but partly. Very good. So let's take a look at the exercise sheet 2. Professor Mattis continued or finished the lecture this week, yesterday, and also continued with lecture 4, so Bitcoin script. And I think this exercise sheet is not that interesting. It's a rather high-level discussion. It's a lot of repetition from the lecture, just to get a little bit of better understanding of what's going on. And then we take a look at the next exercise sheet. So I only see 4 people in the Zoom meeting, 2 of who I am, with my iPad and my computer. So if you guys want to say something, just raise your voice. Otherwise, I will just do the exercise on my own, because I don't think it makes too much sense to wait for anyone to answer the questions. Let's check what you guys want to talk about in terms of exercise 2, 6, 7, 8, 4, 5, 9, 7, 9, Genesis block, memory pool, 7, 8. So emphasis on the last questions here. Very good. Then let's go into it. I'll zoom a little bit for me, otherwise I don't see it here. Very good. Okay, exercise 2, name the 3 key properties of the Bitcoin blockchain according to the lecture and explain them. So this is a very easy one. When we go through the slides, you will see them. It's not that difficult here. So the 3 key properties are, the blockchain is first of all trust-free. So we don't have a third party we need to trust or which maintains the platform. So the decentralized network is basically on its own, and we through the sheer amount of participation, we can ensure that this is not controlled by a centralized instance. The second property here is the blockchain is tamper-proof. So no one is able to manipulate data after it is written or stored on the blockchain. So that's also very important. As I showed in I think last week, we discussed a little bit about this lock structure. So all the actions or all the transactions that happen on the blockchain are stored in it. So that's very, very important here. And the third one is that the blockchain is transparent. So a blockchain which is not transparent in terms of you cannot check which contents are in there is not a blockchain or should not be used. Why? Because there is no integrity proof. So there are some public chains out there which missed the first 100 blocks. No one knows what happened in these first 100 blocks because the owners kept them to themselves. And that's obviously a very bad practice. So transparency is a very important point because you want to be able to understand all the contents here. So trust-free, tamper-proof, and transparent. Decide if changing the following contents of the block alters the hash of the block header. So this is something where I would like to look into the slides because I think that's an interesting part here. because we had this quite nice in the slides here. So let's do it like that, do it like this and that. Very well. So what you see here is the slide 8 of Bitcoin Basics, and this really depicts very good what is included in a block header and what is used for the hash of the block header. So that might be a little bit confusing, but so transactions are not in the block header and everything else is in the block header, but for example, the block size and the transaction counter are not part of the hash of the block header. So what you see here is we have color coding. So this dark gray stuff is included. This little bit light gray is not included in the hash. So the block's hash used for chaining is calculated from the version until the nonce field. So version, hash of previous block header, hash of Merkle root, time, difficulty, nonce is included in the block header. And now we need to think about if changing contents alters the hash of the block header. So it's not that difficult. So you look at what I'm asking and you look if it's in the block header or not, or in the hash of the block header. So transaction ordering, transactions stay the same. So when we think about that, we look at the transactions here. So transaction can be ordered as we like, because there's no rule how we need to order them, and except one simple rule but that's not important for it now. We can arrange them as we want. And so it should not influence the block header because it's not in there. So, and that's wrong because we need to look at what, that we are not directly in the block header, but we are indirectly in the block header. So the hash of the Merkle root is the hash of the Merkle root of all transactions. So if we newly arrange the transactions, recalculate the Merkle tree, then also the hash of the Merkle root changes and therefore the hash of the block header. So first answer here for if the contents of the block alters the hash of the block header, transaction ordering does actually change the block header, the hash of the block header. The second thing is transaction add removal. So if we add new transactions, if we remove new transactions, does this change the hash of the block header? Same thing here. It's not directly changing it, but indirectly, because if we add new transactions, remove transactions, then actually the Merkle tree changes, the hash of the Merkle root changes, and therefore the hash of the block header also changes. The difficulty is a little bit simpler because if you look here, it's directly in this hash marked. So yes, you can change it and it would influence directly the hash of the block header. The problem here is you cannot really change it because it's defined by the network. So that's you could change it, but you would make your block invalid. What about previous blocks? Previous blocks, you can also could switch it out because the hash of the previous block header is included in your block head hash, and would change, but it's also something you cannot change directly because you would invalidate these earlier blocks. And last but not least, the nonce itself is like this number only used once, so that's the abbreviation. And this basically allows you to say, this is basically your retry for the mining puzzle or for this hash puzzle. And you can change it, and it definitely would change the hash of the block header, and that's exactly its purpose. So the purpose of the nonce is to be able to easily change the block header. So we got one question, and I think that's to repeat that for that person. The question is, I don't really get why the transaction ordering and the transaction adding removal is relevant. You mentioned that only the dark gray area part of the block header transaction are not included somehow there. And this is exactly what is the key here. So the transactions are not included directly, but are indirectly included, because as you know from these, I don't have it here right now, but in terms of, let me just draw it for 1 second. So if you have your header, there is a lot of stuff in there. We don't care right now, and there is this root tree, this root hash. And this root hash is basically the root hash of this Merkle tree. So all this calculation, you have to look at the slides if you want to see how they work. Not too complicated, stuff like that. And going on there, these are at the leaves are all these transactions. So if you, for example, remove transactions in terms of, okay, you cancel this one, or you swap these ones, then you need to recalculate all these intermediate hashes here. These need to be recalculated, these ones, stuff like that. All, and in the end, this one is also changed. And that's the important point here. So adding transaction leads to the fact that the hash of the Merkle root changes, and therefore the hash of the block header changes. That's the important part here. So let's continue with the questions here. Third question, explain how chaining is implemented in a blockchain. Also a very easy question. It's just a repetition. So you basically say we chain blocks with adding the hash of the previous block header to our current block header. Exactly as you would see here in the PowerPoint with the hash of the previous block header here. Continue with the Genesis block. Or maybe first of all, answer the questions from Tweetback. Because in the end, yeah, I think answering questions is, if it helps, then we should do it. So I think there is a little bit of misconception of how we create blocks. So first of all, when we create a block, we take all the transactions we want to include. We include the previous block header we want to build up on. We include our own Coinbase transaction so that the mining reward is paid to us, stuff like that. And then when we have kind of a valid block, we can start solving the mining puzzle. So first of all, we build the regular block and then the mining puzzle. And that leads to the fact that obviously if you would change something to a block after you solved the mining puzzle, then your complete work, the work that got into this mining puzzle is gone now. So the block is again not valid anymore in terms of the mining puzzle. So that's very important. But this is these exercises are giving just an idea of what you have to incorporate there. Because imagine if transactions would not be in the block header. So you have to think about the implications here. So if we would answer this question up here in terms of, okay, transactions ordering is not important and transaction add and removal is not important or is not included in the overall blockchain, what would this mean? This would mean that we are able to add and remove transactions retroactively because they are not in the blockchain. They are not integrity protected through the blockchain. And this would defeat the complete purpose of the blockchain. So if transactions are not included in our blockchain, what are we doing? Yeah, so that's the important part here. And that's the real key ingredient here to think about. We need to understand here everything we want to have integrity protected, everything we want to build upon, because we build up on the transaction. So how are we supposed to know if transactions are if someone has money or not, if we cannot agree on which transactions have happened and which not? So that's the very important part here. Also, first question, what to do if you want to analyze the whole history of the blockchain? If I start at the most recent block, how will I know the previous one? I have only the hash of the previous block and no way to unhash it. Oh, thank you very much. This question also has been answered already. Very good. Sorry, did not see this. Okay. So transaction ordering affects the Merkle root, and because it affects the Merkle root, it affects the block header hash. That's exactly what's going on here. So let's continue here. Genesis block. Discuss reasons why Satoshi Nakamoto might have included a message or a newspaper article in the Genesis block. In which field did he store the information? So just to recall, let's look back at Chrome here. This is exactly what they did here. That's where also Satoshi Nakamoto included it. Now let's go to the first block, then you see it. Block 0. And that's the times 3rd January 2009, Chancellor on brink of second bailout for banks. So why would he do this? There are two reasons why this would happen. This is also what Professor Mattes told you in the lecture. First of all, could be a political message in terms of, okay, Bitcoin is there because this banking system breaks down. And the second reason could be that to prove that this block 0 was not proposed before the date. So he could not created this block on the 2nd of January 2009 because then the newspaper article was not out there. And so that's a little bit the idea here. In which field did he store the information? So this is also what is in here. And I want to go a little bit in this because Coinbase data seems a little bit imprecise. And I think we can talk a little bit about that in more detail. So let's get back to this transaction here. And this transaction here had some, this was input, this was output. So as I said before, these are the inputs where comes the money from, and outputs is where the money is going. So, and I also said in Coinbase that we do not have an input because it's the mining reward plus transaction fees. So this is empty. So this is empty means it can be empty, but it does not have to. And the good thing is here for this transaction where the input is empty or can be empty, the Coinbase transaction, we can put arbitrary data in there. So in our input, we can put, I think, 100 bytes, whatever we want, or not whatever we want. The miner who proposes the block can do whatever he wants. And this is where Satoshi Nakamoto put the times 3rd of January, this newspaper article, and where also in block 629,999, this information was posted in there. One second. Sorry for that. Okay, let's continue. 5th question here. 10 years after the first Bitcoin block, the first page of the Times looks like the following. So the Times had some interesting articles, but also down here, BitMEX published following. Thanks, Satoshi, we owe you one. Happy 10th birthday, Bitcoin. And you're now a cryptopreneur, and you decide to start your own coin on the day the newspaper came out. You want to do the same as Satoshi Nakamoto and include a headline in your Genesis blog. Why is it a bad idea to include "Thanks Satoshi, we owe you one" in your Genesis blog? Very good question. So this one here is kind of a trick question. I stole from Twitter actually, and I think it's a very good one because it shows you that the idea here is Satoshi Nakamoto with his headline, with his New York Times, with his Times chancellor on yeah, you know what I mean. And he could not predicted that. Besides, he would be like a journalist at the Times then, but he was not able to include that beforehand. And with this down here, this is an advertisement which is planned days before. So BitMEX, for example, or you would be able to fake that to say, okay, I'm including an ad there, and I'm including this in terms of, okay, I am showing to the world that I did not create this blog before that time, but actually, as you knew this information beforehand, you would be able to produce blogs way before that time. So that's the part here why you should not do this and stick to some other headlines here. And also there's a lot of discussion going on there, so if you want to be extra sure, you should include several headlines of several papers there. And so there are several questions, and I think maybe the same person asks again, but how many transactions are in a block? I'm going to answer this briefly. There is a overall capacity limit of 1 block per of 1 megabyte per block. And this can roughly be translated to around about 1,500, 2,000, 2,500 transactions. It really depends on the size of the transactions. So as a transaction can have an arbitrary amount of inputs and outputs, the size of the transaction can also be some larger and smaller. So that's the reason why there is no exact number to that. Question 6. Name and briefly explain 3 roles in the Bitcoin network. So this is exactly as in the slides. We can briefly jump to that. I think to say it again here. 3 roles. So these are 4 roles. Obviously, we're going through all 4 of them. Let's take a look here. So you as a user are basically a wallet owner. So a wallet owner in terms of, okay, you control the private keys to your transactions, to these unspent transaction outputs. And you own these coins. And if you want to spend the money, you need to sign and publish transactions into the network. Miners will pick them up, full node will pick them up, and miners will eventually include them in blocks. Lightnode is a software rarely used anymore. So for example, IoT devices do this. Mobile apps could also rely on that, but it's much more easier to build centralized solutions. Lightnodes could basically be seen as a software which communicates with one full node to obtain information about transactions and basically to have one connection to the network to relay transactions to. That's a very easy and cheap way of getting the information. Okay, what is happening on chain with my money, and second of all, to have regular wallet functionalities. The full node is also a node in terms of it stores and keeps the complete blockchain. So the idea is that a full node is a 24/7 running computer server which stores all that, connects to other full nodes, to other miners, to light nodes, and exchanges data. obviously it validates every transaction and every block and relays everything further. So people always ask, why would you do that, or why would you set up a full node without getting any money? And the reasons are there are many reasons. So one reason would be, for example, you are a data scientist and you want to look into the Bitcoin blockchain. Valid reason. You're an exchange and want to know about your user funds. Valid reason. You want to have you're a payment provider for Bitcoin. You want to have a fast connection to the Bitcoin network. Valid reason. So there are so many valid reasons. You are a Bitcoin fanatic and want to support the network by running your full node. Valid reason. So there does not have to be any monetary reasons, but other reasons as well. And the miner, last but not least, is is the same as a full node, but what they do is they produce the new blocks. So they take a look at the mempool, the transaction pool, take the newest transactions or the transactions with the highest transaction fee, include them in a block, and try to solve the mining puzzle there. And that's the idea here. These are the four answers, the four entities in the network. No, that's wrong. Where is it? There. Okay. So my colleagues are answering some questions on Tweetback. So let's see if there is something we should answer on stream. Yeah, that's fine. Okay. Continue with the next question here. Explain the function of the memory pool. So actually I just did, but let's go over it. The memory pool is if we look at the slides here, I think that's should be in here. The memory pool is a local file in your full node, or respectively on your miner if you're a miner. And the memory pool, the idea is that because a block is created every 10 minutes, we cannot include the transaction directly into the blockchain. So we need some kind of waiting room for the transactions. It could also be the case that there are too many transactions to directly put into a block and they need to wait for 10 more minutes or several hours, depending on the network load. And this memory pool is basically filled with transactions you as a full node receive from other full nodes or miners. So a new transaction gets created, it's sent into the network and distributed there in terms of, okay, hey, here is a new transaction, please include if you mine a new block. And this really leads to the fact that all these transactions stored in the memory pool. And what the miner does is basically they take the transactions, sort them descending by transaction fee, and take the transactions until the block is full, so to say. And that's the main idea of the memory pool. It's a store for transactions which are not included in the blockchain. So let's check the solution here, that I'm not telling any lies. The memory pool stores all transactions which are not contained in a block yet. Each full node maintains the list of these transactions and updates it when a new block arrives and when new transactions arrive. So in terms of a new transaction arrives, block mempool gets fuller and fuller and fuller. When a new block arrives, then your software, your full node, checks if transactions which are in the memory pool were included in the block, and then they are removing them from the memory pool because they are already included in the blockchain. So that's the idea here. Yeah, so there's a question. I think we can go a little bit into that because we do not do this in the lecture. So would you please explain about bundlist fee estimates and peers in blockchain? So this is not too complicated, so we grade it out because we do not explain them explicitly here, but as a short off-topic, peers is your list of nodes you are connected to. So you are connected to roughly 8 or 10 nodes in the network, and to reconnect upon when your server goes down or restarts, you want to reconnect to them, so where you store IP addresses and ports in there. The ban list is for nodes which behave not nice. So if you receive blocks which are invalid, if you receive transactions which are invalid, you ban this node and search for other ones, because you don't want to communicate with them anymore. And fee estimates is a file generated by your local Bitcoin client to be used by other by your wallet, in terms of how what are fees you should put in your transaction to get it accepted in a certain time frame. So that's a little bit of a detail here, but quite interesting. Okay. Let's check this question. Someone has a little bit of trouble of understanding. Since every block has a Merkle tree, can we assume that the block size equals the amount of Merkle trees on the blockchain? So the Merkle trees itself contain the transactions. So if we would argue about that, all transactions in the Bitcoin blockchain roughly make up the overall blockchain. Yeah, so transaction volume or the transactions is the core of Bitcoin. So that's what's stored in there. But obviously a lot of integrity information is stored there. A lot of mining puzzle information is stored there. So it's not totally correct what he's saying. But the block size, one block is roughly the size of the block is heavily dependent on the transactions in this block. So this is the part which takes the most amount of storage in a block. So one block is mostly made out of transactions. Yeah. Okay, let's continue. And what about the block height? It doesn't have to do anything with the block height. So maybe you can write your question in Moodle, and then I can discuss this a little bit further with you there. Okay, let's continue. Let's go back to Foxit, and Alice wants to send one BTC to Bob. What steps does her transaction take until being completed? So let's look a little bit into that. I think there's a really nice slide also here. You see this is a very slide intensive exercise. So first of all, the animations are broken here. I'll have to fix that. First of all, the transaction is created and signed by the wallet owner. So to create a transaction, you need to select your own transaction outputs you want to spend. You need to create the new transaction output. So Alice, for example, needs to obtain Bob's address. Otherwise, she won't be able to send him money. But that's, I think, implicitly, you can think about that. You have to sign it, obviously, with your private key. Then you take the transaction and send it to a full node. So full node is connected in the network, can validate the transaction, and can spread it out into the network. Every node who receives this, or every full node and miner who receives this, is storing the transaction in the memory pool. And eventually a miner will take the transaction and put it in a block and solve this block. So creates a proof of work on that, and when the block is valid, it's transferred to the network. And other nodes validate the block, update the memory pool, so they remove the transaction from Alice to Bob from the network and start over. That's it. It's easy as that. Okay, let's continue. storing Bitcoins. Last question for this exercise sheet. What is the difference between a hot storage and a cold storage? Give an example for both types. Which type do exchange wallets fit in? So I think that's a very that teaches you a little bit about security and about how to keep your own Bitcoin safe if you buy some or if you have some. And I think it's very important to understand the difference here, because hot storage and cold storage are two very different approaches of how to secure your keys. So saving or securing your Bitcoins comes down to one thing: keeping your private key private. And a hot storage basically means that the private key is somehow immediately available. It's stored on your phone, on your computer, it's maybe password protected on your computer, but typing the password in, it's immediately available to sign transactions and to spend the Bitcoin, which is very good for you because you can send Bitcoins around very fast, but it's very bad also for you because the downside is that if your computer gets hacked, if your password is, if it's not password protected, stuff like that, other people could spend your Bitcoins very easily. So that's very, very dangerous. And a lot of hacks have happened. A lot of money got lost this way. Cold storage means that the private key is securely protected, is protected somewhere which is not connected to the internet. So you could imagine you could write a text and put it in some kind of safe in your bank, resulting in it's not really easily accessible, but it's also not accessible for malicious parties. So that's the very difference. Yeah. So people correct me on tweetback. I thought hot storage was related to being connected to the internet. Yeah. So that's sorry for that. So that's what I meant with being available quickly. So you do not need to connect some information to the internet. You don't need to type the text into your computer, stuff like that. So that's what I meant by that. So which type do exchange wallets fits in? Funnily enough, both. If you talk to exchanges, or if you read their security measures, they are very paranoid. Why are they very paranoid? So because they have a big red crosshair on their servers. So you could imagine if you deal with funds worth billions of other people's money, you want to make sure that the money is not gone or lost. So what exchanges do is they split the money up in a large portion into a cold storage, into a cold wallet, and only the money they need for withdrawals, for example, this is put in hot wallets. So you could, for example, Binance is a exchange which does this very often, or is very heavily involved in security. Funnily enough, they lost, I think, 1,000 Bitcoins, I think, last year. And so it's not funny, but it's rather sad that it's so hard to come up with really sufficient protection for all your end users. And yeah, so they got it covered, I think. So they had a SafeFu fund. So they put, I think, 1% of all the transaction fees into a separate banking account, so to say. And in terms of they got hacked, that they could use this money to reimburse their customers. One question here: is a local wallet software like Electrum considered cold or hot? So this is a local wallet software in terms of you install on your computer. The computer is connected to the internet. It's hot. If it's a machine which is not connected to the internet, and maybe you created transactions locally on a not connected to the internet computer and transfer this transaction via USB stick, for example, that could be considered as a cold storage.